Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this lesson we're going to look at Year 1 Hess's Law, looking at different Hess's laws such as enthalpy changes of combustion, enthalpy changes of formation, enthalpy changes of reaction, and then using these principles to apply this to any unfamiliar enthalpy cycle. So to start off with, we need to understand that Hess's law is a law that describes that the total enthalpy change of a reaction is always the same no matter which route is taken. This is a bit like ascending a mountain. You could either take the most direct route up from the bottom to the top, or you could take the longer winded route up, which would be easier, but in both cases you end up having the same gravitational potential energy irregardless of the route taken. And so this is akin to displacement and distance. Here the distance for the red line is shorter than the blue line. However, displacement wise, from the start to the finish, they've ended up in the same space. So reactions are similar. You can either go straight for something or undergo stepwise processes, and it will give you exactly the same energy change. For example, here we've got nitrogen dioxide. This can undergo decomposition to form nitrogen gas plus 2 moles of oxygen. However, it can also undergo decomposition to nitrogen monoxide plus 1 molecule of oxygen. And then this can then undergo decomposition to the elemental form. To link this to enthalpy change, we should remember from previous videos that enthalpy change is delta H. And whenever we've got a reaction, then we can call it delta HR. Now, there are certain reactions that have their own subscript here, such as combustion, where it's a C, and formation, where it's an F, and neutralization, when it's NEUT. However, generically, they are all just types of reaction, so they can all fit into the same concepts that we're going to be discussing for delta HR. But we'll look at this in more detail later. So imagine the enthalpy change for nitrogen dioxide going to nitrogen oxide is a delta H, and it is worth plus 114 kilojoules per mole. So that is going from this starting position to this position. That is obviously an endothermic process, hence the positive delta H, and so it's costing 114. Forward, if we then take that nitrogen oxide and decompose it further, then the delta H of this value is minus 181 kilojoules per mole. Now, with those two pieces of information in hand, we can actually work out what this is, delta HR. If we weren't able to get this information, we can use this principle of the idea that no matter where you start and you'll finish, the energy will be the same. So if this is our starting position here, and I just want you to think of it as a start position, then our finish position is here. And irregardless of the route that you take, whether it be from here directly to here, which is this enthalpy value, or if you go this way around, they are going to come up to be the same number. So route 1, going from start to finish here, is exactly the same as route 2. Going from start via here and up this way. And so mathematically this looks like this, 1 equals 2. To look at this further, delta HR is route 1, so we've got delta HR here. So route 2 is to first of all go along this arrow here. Now this arrow collectively is worth plus 114. And it's worth stopping to think about what happens when we're going with the arrow in terms of the direction that we're taking, or if we go against the arrow. Now, if we're going with the arrow, then whatever this value is, in front of it, you put a plus. So because this whole arrow is worth plus 114, we're going to put plus 114 here. And then because we're taking the same direction as the arrow, going in, because we're trying to get this route round, and we're going with the arrow here, and we're going to put a plus in front. So we're currently at this point here. We need to take one more stepwise to get to our finish point. And again, we're going with the arrow, and because we're taking the same direction as the arrow, we put a plus in front. So it's going to be plus, and then the value of this arrow altogether is minus 181. So we put that in brackets, and it's really important to keep the values of each arrow in brackets. The main error most students make with Hess's Law is they get the signage wrong. But if you follow these rules, okay, and keep the actual enthalpy values in brackets, then you can't really go wrong. Now, just for completion here, if one of these arrows were pointing in the wrong direction, then as we went from start to finish, imagine this arrow was pointing upwards, then you would basically put a minus in front. So if you take a different direction to the arrow, you put a negative in front. So instead of plus here, it would have been a negative. We'll look at examples of this later on in the video. So all that remains is to carry out this calculation, and that works out to be minus 67. And so because of the values, obviously here were kilojoules per mole, then this would also be kilojoules per mole. And so what you've used is this idea that the reaction enthalpy changes are always the same no matter which route is taken, to work out the value for this, which was route 1. So typically a reaction involves reactions going to products, and we call this delta HR. Now if we change those reactants to be specifically elements, which I'm going to use as E, and those products always being something that is a compound, so more than one type of element, then we give this a specific designation, and this designation is delta HF, which is the enthalpy change of formation, and it's the formation of our compound, which we're just calling C for this, from elements E. And this leads into the definition for delta H formation, or the standard enthalpy change of formation. It's where 1 mole of a compound is formed from its elements under standard conditions and with standard states. An example being the compound methane. So this is a compound because there's more than one type of element in there. And so the elements that methane is made up of is carbon, which will be in its most standard state, which is chosen as graphite, and hydrogen, which is gas under standard conditions. And so because we've got obviously 4 hydrogens on the right hand side, we need to put 2 in front. And so this is an example of delta H formation, and this value has for it minus 15.8 kilojoules per mole. Here's one for you to try. We're going to make bromomethane, CH3Br. Pause the video now and have a go at what elements this compound will be made up from. The elemental form of the Br, the bromo, is going to be bromine, and remember it's diatomic. Obviously, because we only have 1 bromine in the actual bromomethane, then we're going to have only half of a molecule of bromine. In terms of hydrogen, we have 3 hydrogens in the product, but it exists diatomic as H2, so we can have 3 halves of a hydrogen molecule, and then we've got 1 carbon, so we can have 1 carbon there. And so this is the overall balanced delta HF for bromomethane. So usually an Hess's cycle that shows the enthalpy change of formation involves reactants going to products in this direction. But obviously reactants and products themselves can be compounds and so can be formed from elements. Okay, so thinking back, if we think that both reactants and products are just rearranged versions of the atoms that are in reactants, so they will both contain the same elements in them. And so the same elements make up the reactants as do the same elements make up the products. And therefore we get a triangular cycle where elements are the linking factor between the reactants and the products because they all contain the same atoms. So reactants going to products is called delta HR. And then because this is a specific type of product, elements forming reactants, if they're compounds, then we have delta HF. And then if those elements going into products, that is also a separate formation on that arrow there. So take, for example, this reactant going to these products here. Now you can see this is a compound because they have different elements. This is a compound, but this one is just an element, 3 sulfur moles of sulfur. We'll come back to this in a moment. So the elements that make up all of these reactants and products combined are 3 sulfurs. We've got 2 moles of hydrogen gas, and then we've got a mole of oxygen. And so because these are the same elements that make up the reactants and the products, we can link those together by putting arrows like so. So imagine our job in the question is to work out what delta RH is of this arrow here. So going back to our original idea, this is our start and this is our finish. Then we are expected to know some information that allows us to basically understand what the values of these two arrows are. So first of all, if we know that the formation of sulfur dioxide is worth -297, then because we have 1 mole of sulfur dioxide here, we can label up that we have a -297 for this arrow. And that's telling us that the formation of 1 mole of sulfur dioxide from these elements is worth -297, going from start to finish here. If we are then told that the formation of dihydrogen sulfide is -20, then that's telling us the formation of 1 mole of SH2, because remember it's kilojoules per mole, is -20. So to correct for the fact that we have a 2 in front of our balanced equation here, then we are going to need to understand that the -297 of the sulfur dioxide plus 2 lots, and that again, just to reiterate, is due to this value here, 2 lots of -20 for the 2 dihydrogen sulfides that are produced. And so collectively, that is the value for this whole arrow here. So if we go from here to here, the magnitude of that arrow is worth this amount. So the final bit of information that we need to know is what H2O is, and that works out to be -286. And this allows us to start working out this arrow here. So we've got 2 moles of water here, due to the big 2 in front of here. So I know that we need to have 2 times -286 on this arrow here. Now it's worth noting that the reason I'm happy at this stage and know that the magnitude of the arrow is just this value here is that the sulfur is an element, and it's come from an element. Because the definition of an enthalpy change of formation is the formation of 1 mole of a compound formed from its elements, if we're taking an element and making an element, then the actual value of this for the formation is completely 0 because nothing has changed. So therefore, I don't need to account for sulfur in my calculation here because it's an element from an element, there's been no change. So all that remains is to think back to what I'm trying to work out is my start to my finish. So this route to work out delta RH is going this direction here. The alternative, longer-winded pathway I could take is to go via the elements and then recombine them to make the products. So we could go route 2, could be going this way around. So we're going to label that as 1 and this route as 2. So we're trying to work out what 1 is because that's our delta RH. So if we start at this point, and if we're trying to work out this arrow, then I'm going to go against this arrow. So initially I need, because I'm going against the arrow, we're going to put minus in front. Then I'm going to work out what the sum of this is in a calculator. So I'll do this all together. And that turns out to be altogether minus 337. So keep that in brackets and put that here. And then we're at this point. And then the next stage is going with the arrow. So because we're going with the arrow, the next component is going to have a plus in front. And then we're going to work out in a calculator what the sum of 2 times minus 286 is. And that works out to be minus 572. So we put that in brackets. Again, just to remind you that most students make the mistakes here by not using the brackets really carefully. And putting all this into a calculator, we get the answer of minus 235 kilojoules per mole. So now it's time to put some of this theory into practice. Pause this video now and attempt this question. Okay, so if your answer was A, then you've correctly used the methodology that we've just talked about. Just to quickly go through it, if we've got our elements at the bottom, which in this case would be carbon plus nitrogen plus oxygen, then these elements either produce the products or the reactants, they're the same thing. On this side here, we have our ammonium nitrate, which for each mole of it is worth minus 366. So because we have 2 moles of that, it's 2 times minus 366. Obviously the carbon and the carbon are exactly the same, so there's no value, hence why there's no value in the data table. On the other arrow, we have 4 moles of water, and we have 1 mole of carbon dioxide. We also have 2 moles of nitrogen, but again, because nitrogen and nitrogen are the same, there's no data for that. So if we populate that arrow, the 4 lots of the minus 242, plus, because of our 1 mole of carbon dioxide, the minus 394. And because we're trying to work out this arrow here, then our start point is always the side of the arrow that doesn't have the double-headed arrow. So because this here, this is our start point. Whereas the finish is always where the arrow has that double-headed part. So this is our finish. And so this is route 1 that we're trying to work out, and we've got the data for route 2. So we're going to start route 2 at the same start point. We're going to go down here and then up here. And this is route 2. So route 1 equals route 2. Because we're going against the arrow, we're going to put, for route 2, a minus in front of the 2 times the minus 366. And then because we're going with this arrow, we're going to put a plus in front. And then put everything in this arrow together. So sometimes I like to just put all the arrows together to make sure when I punch it into a calculator, I'm not going to make any issues with signage. And remembering, because we've got this extra brackets, to put a secondary closed brackets there. And as long as you punch this into the calculator exactly as it comes here, you should come up with minus 630, which equates to multiple choice A. Problem I often see with students is not putting this in exactly as you write it down. Issues with brackets, and then also just being really aware of the direction of the arrow. So obviously, because we went against the arrow here, we had a minus here. Because we went with the arrow here, we had a plus here. So now I want you to pause the video here and try this exam question. You're given an equation and you're given the data required. Okay, so we're going to start to have a look at this and just break it down step by step so that you can check that you got an answer of plus 90 kilojoules per mole. If you did, you've been following the correct method. So here we have our reaction, delta RH. And so we'll put this on the top of our Hess's cycle. And we know this is worth minus 2677. And we know we have our elements here. You can just designate these as E. You're not going to get any marks for actually knowing the different elemental types. Or in the actual elemental form we've got here. But as I said earlier, an E would suffice for here. The skill set they're looking at is that you can actually construct and calculate the correct enthalpy changes. So to make this ammonium chlorate from this element here, we're going to use this value here, which is minus 295. We know that we've got 3 moles of ammonium chlorate. So we're going to stick a 3 in front of the minus 295. And this arrow is done because remember aluminium from its elemental aluminium is going to be 0 because there's no formation. Then the alternative is taking these elements and making these compounds here. So we've got aluminium oxide, which is this value here. We've only got 1 mole of it, so we only need to use the minus 1676 once. Aluminium trichloride, again, there's only 1 mole of it here, so we're going to add minus 704 to this side. Then we've also got the waters here. We've got 6 waters, so we're going to put plus 6 times the minus 242 for that. And then the thing that we're interested in is the enthalpy of formation for the NO. So this is going to be plus 3 NO. Now, if you want to think of this as an algebraic expression, then you can make NOx. So this could also be seen as 3x. So you can see that this is a different type of question than the one we looked at previously, because if instead of trying to work out the magnitude of a whole arrow, we're only interested in the component, the nitrogen oxide formation that is within an arrow. However, the same principles apply. Because the arrow of interest is this arrow here, we're going to just designate the start of the arrow as our start point and the end of our arrow as our finish point. And so this is root 1 going upwards here. The alternative is to go round and form this way is root 2. So let's just calculate what the 2 arrows for root 2 equal. So we've got, first of all, this arrow here, which is the 3 times minus 295. And then because we're going with the arrow, there'll be a plus in front of here. And then we're also going with this arrow here. So we're going to put a plus in front of there. And close brackets for this value here. The minus 2677. And so altogether, this equals minus 3562 kilojoules per mole. So knowing that root 2 equals root 1, the whole of the arrow for root 1 here, we know that the 3 minus 3, 5, 6, 2 equals the whole of the brackets here. And this line here is just everything that is included in root 1's arrow from start to finish. So then we want to isolate just the free nitrogen oxide so that we can work out the enthalpy change formation. So each of these, as they go across the equal sign, the signage in front of them will change. So although this isn't stated here, this is a plus, so it will become negative. This is a plus, so it will become negative. This is a plus, so it will become negative. And as we're leaving this on this side, it will be plus 3NO. And so here you can see all of those sign changes as a result of it going across the equal sign. So it's looking rather busy at the moment. If we then put this whole line into the calculator to work out what the sum of that is, then we end up with 270 is what 3 NOs is worth. So finally, 1 NO is 270 divided by 3, which then gives us the total plus 90 for each 1 mole of nitrogen oxide. So this was slightly different from the previous questions, again because we're only working out 1 delta FH within an arrow, but you can see that some simple rearranging of an equation and really NO being algebraic, we've got the right answer. Something just to be really careful of is to always put your enthalpy values, for example this one here, minus 1676, in a brackets, so that then if you did have to rearrange like we did and take it across an arrow, that you are not actually changing the enthalpic value of it, you're only changing basically the direction of it in front. So we've looked at enthalpy changes of formation. The next one we're going to look at is enthalpy changes of combustion. So going back to our original idea, whenever you take a reaction or reactants and make them into products, we call that a enthalpy change of reaction. Combustion is just a specific example of this, whereby your reactants this time taking any chemical species and you're reacting oxygen to it. In doing so, you are producing combustion products. And we call this delta CH, the enthalpy change of combustion. This is defined as when 1 mole of a compound is burned completely in oxygen, so under complete combustion conditions, under standard conditions and with standard states. An example of this might be methane, CH4, that when reacting with oxygen, then we form carbon dioxide and water. And so this has a delta CH of minus 890 kilojoules per mole. It's really worth noting that delta CH, enthalpy changes of combustion, are always negative. Whenever you take any chemical and react it with oxygen, such as Na reacting with oxygen to form Na2O, then what you're actually doing is a combustion reaction. And this would be the combustion for sodium, and we're using 1 mole, and hence why it fits the idea of 1 mole of a compound being burned. So if you have reactants going to products, both the reactants and the products can both undergo combustion. So we could take the reactants, burn them in oxygen, and then we'd get the combustion products for those reactants burning. And then we could also take the products, which is obviously just a rearranged version of the reactants, and burn them in oxygen. And so we would end up with the same combustion products. And so with this constructed Hess's cycle for combustion, if we wanted to work out the delta CH for the product, so this was our question mark, then what we're trying to work out is starting at this point of the arrow. Remember, we will start at the end without a double-headed, and finishing at the double-headed as the finish. Then that's the same, this route 1 is the same as going against this arrow to the reactants and then burning those reactants to form the combustion products. Because we've gone against this arrow, we're going to put a minus delta RH. Because we've gone with this arrow, then we've got a plus delta CH for the reactants. So let's see if you can apply these ideas to this particular exam question. If you'd like to try this, pause the video now and have a go. Okay, so the answer is B, so well done if you got that correct. We're going to show you exactly how to work this out, and it all starts with the idea that we're told this reaction here is what we're trying to work out, the delta RH. The data we've been given is changes of combustion on this column here. So let's start to construct a Hess cycle from that. So the delta RH here is exactly what we're trying to work out. And this data here is all due to the combustion of these different substances we've got here, here, and here, which relates to here, here, and here on our equation. So all we've got to do is very quickly construct a diagram that the arrow's in the correct direction. So we burn carbon, we're going to form carbon dioxide, so 4 CO2. And then we've also got 5 waters on combustion of the hydrogen. So this is in excess oxygen, although that isn't really necessary for any of the marks, etc. So taking the data from this, we've got 4 moles of carbon, so we're going to need 4 times the amount here. And we've got 5 moles of hydrogen, so we're going to need 5 times the amount of here. And remember to put all that in brackets because that whole sum equates to this arrow here. Then finally, we've also got this arrow here. If we combust butane, which equates to this value here. And again, remember to put it in brackets so that if you have to do any manipulation and rearranging equations, the signage carries over. So we've been asked to work out delta RH, so the start of our arrow is here. And then if we just have S for that, and then our finish of the arrow is here. So that's route 1. The alternative is to go this way around, which is route 2. So 1 is the same as route 2. And so we're going to go down this arrow here. So we've got because we're going in the same direction, we've got plus the sum of this whole brackets here, which when you put that into a calculator, works out to be minus 3003. And then we're going against this arrow, so we're going to put a minus as a result. And then put in the value for that bracket. And then put this into the calculator, remembering to keep all enthalpy within brackets, and you will get out the correct signage of B minus 126.5. Now to sum all this up, this is the final exam question. Please pause the video now, have a go and see if you can get all 3 marks. Okay, if you got minus 3,320 kilojoules per mole, that's the whole 3 marks there. And if you didn't, I'm going to quickly show all the workings out on one screen so that you can see exactly where you went wrong. And so that concludes our lesson on Year 1 Hess's Law. So firstly we looked at formation, then combustion, and then finished on an exam question of an unfamiliar enthalpy cycle